After climbing heights, we now dive into the depths of the oceans and see how the body adjusts to the environment in the deep. There are basically three important factors that causes physiologic derangements as an individual descends into the depths of the Earth's oceans. Number one is the effect of depth on pressure. Number two, the effect of depth on the volume of the gases in the body. And three, the effect of depth on the inspired nitrogen in the gases that divers inhale. When human beings descend beneath the sea, the pressure around them increases tremendously. A column of seawater 33 feet or around 10 meters deep exerts the same pressure at its bottom as the pressure of the atmosphere above the sea. Therefore, a person 33 feet beneath the ocean surface is exposed to 2 atmospheres pressure, with 1 atmosphere of pressure caused by the weight of the air above the water and the second atmosphere caused by the weight of the water. At 66 feet, the pressure is 3 atmosphere and so forth, as seen in the table to your left. Another important effect of depth is the compression of gases to smaller and smaller volumes. At 33 feet beneath the sea, where the pressure is 2 atmosphere, the volume has been compressed to only a half liter, and at 8 atmosphere, or around 233 feet, it has been compressed to 1/8 of a liter. Thus, the volume to which a given quantity of gas is compressed is inversely proportional to the pressure. This principle of physics is called Boyle's law, and it is extremely important in diving physiology because increased pressure can collapse the air chambers of the diver's body, especially the lungs, and may cause serious damage. About 4/5 of the air is nitrogen. At sea level pressure, the nitrogen has no significant effect on bodily function, but at high pressures, it can cause varying degrees of narcosis. When the diver remains beneath the sea for an hour or more and is breathing compressed air, the depth at which the first symptoms of mild narcosis appear is about 120 feet. At this level, the diver begins to exhibit joviality and loss of many of his or her cares. At 150 to 200 feet, the diver becomes drowsy, and at 200 to 250 feet, his or her strength wanes considerably, and the diver often becomes too clumsy to perform the work required. Beyond the 250 feet, or around 8.5 atmospheres pressure, the diver usually becomes almost useless as a result of nitrogen narcosis if he or she remains at these depths for too long. Nitrogen narcosis has similar effects to those of alcohol intoxication, and for this reason, it has frequently been called ruptures of the depths. The mechanism of the narcotic effect is believed to be the same as that of the most other gas anesthetics. That is, it dissolves in the fatty substances in neuronal membranes, and because of its physical effect on altering ionic conductance through the membranes, it reduces neuronal excitability. When a person breathes air under high pressure for a long time, the amount of nitrogen dissolved in the body fluids increases. This is because blood flowing through the pulmonary capillaries becomes saturated with nitrogen to the same high pressure as that in the alveolar breathing mixture, and over several more hours, enough nitrogen is carried to all the tissues of the body to raise their tissue nitrogen partial pressure to equal the nitrogen pressure in breathing air. Because nitrogen is not metabolized by the body, it remains dissolved in all the body tissues until the nitrogen pressure in the lungs is decreased back to some lower level, at which time the nitrogen can be removed by the reverse respiratory process. However, this removal often takes hours to occur and is the source of multiple problems collectively called decompression sickness. This diagram illustrates the principles underlying bubble formation. In Figure A, the diverse tissues have become equilibrated to a high dissolved nitrogen pressure, about 6.5 times the normal amount of nitrogen in the tissues. As long as the diver remains deep beneath the sea, the pressure against the outside of his or her body compresses all the body tissues sufficiently to keep the excess nitrogen gas dissolved. However, when the diver suddenly rises to sea level, as seen in Figure B, the pressure on the outside of the body becomes only 1 atmosphere, while the gas pressure inside the body fluids is the sum of the pressures of water vapor, carbon dioxide, oxygen, and nitrogen, or a total of 4,065 millimeters mercury, 97% of which is caused by the nitrogen. Obviously, this total value of 4,065 millimeters mercury is far greater than the 760 millimeters mercury pressure on the outside of the body. Therefore, the gases can escape from the dissolved state and form bubbles composed almost entirely of nitrogen, both in the tissues and in the blood, where they plug many small blood vessels. The bubbles may now appear for many minutes to hours because sometimes the gases can remain dissolved in the supersaturated state for hours before bubbling. The symptoms of decompression sickness are caused by gas bubbles blocking many blood vessels in different tissues. At first, only the smallest vessels are blocked by minute bubbles, but as the bubbles coalesce, progressively larger vessels are affected and tissue ischemia and sometimes tissue death result. In most people with decompression sickness, the symptoms are pain in the joints and muscles of the legs and arms, affecting 85 to 90% of persons who experience decompression sickness. The joint pain accounts for the term bends that is often applied to this condition. In 5 to 10% of people with decompression sickness, nervous system symptoms occur ranging from dizziness in about 5% to paralysis or collapse and unconsciousness in as many as 3%. The paralysis may be temporary, but in some cases, damage is permanent. Finally, about 2% of people with decompression sickness experiences the chokes caused by massive numbers of microbubbles plugging the capillaries of the lungs. This condition is characterized by serious shortness of breath, often followed by severe pulmonary edema and occasionally death. Breathing large amounts of oxygen under pressure during deep dives may also have detrimental effects. Molecular oxygen has little capability of oxidizing other chemical compounds. Instead, it must first be converted into an active form of oxygen, mainly in the form of oxygen-free radicals. Even when the tissue partial pressure of oxygen is normal at the level of 40 millimeters mercury, small amounts of free radicals are continually being formed from the dissolved oxygen. Fortunately, the tissues also contain several enzymes that rapidly remove these free radicals, including peroxidases, catalases, and superoxide dismutases. Therefore, as long as the hemoglobin oxygen buffering mechanism maintains a normal tissue partial pressure of oxygen, the oxidizing free radicals are removed rapidly enough that they have little or no effect in the tissues. However, at very high levels, the amount of oxidizing free radicals literally swamp the enzyme systems designed to remove them, and now they can have serious destructive and even lethal effects on the cells. One of the principal effects is to oxidize the polyunsaturated fatty acids that are essential components of many of the cell membranes. Another effect is to oxidize some of the cellular enzymes, thus damaging the cellular metabolic system severely. The nervous tissues are especially susceptible because of their high lipid content. Therefore, most of the acute lethal effects of acute oxygen toxicity are caused by brain dysfunction. When the partial pressure of oxygen in the blood rises above 100 millimeters mercury, the amount of oxygen dissolved in the water of the blood increases markedly. The extremely high tissue partial pressure of oxygen that occurs when oxygen is breathed at a very high alveolar oxygen pressure can be detrimental to many of the body's tissues. For example, breathing oxygen at 4 atmospheres will cause brain seizures followed by coma in most people within 30 to 60 minutes. The seizure often occur without warning and for obvious reasons are likely to be lethal to divers submerged beneath the sea. Other symptoms encountered in acute oxygen poisoning include nausea, muscle twitchings, dizziness, disturbances of vision, irritability, and disorientation. Exercise greatly increases the diver's susceptibility to oxygen toxicity, causing symptoms to appear much earlier and with far greater severity than in the resting person. So what are the measures to prevent decompression sickness or address hyperbarism? One is for rapid recompression in a pressure chamber followed by slower decompression. Thus, one is like stimulating what would have happened if the diver was decompressed slowly. This reduces the volume of the bubbles and forces them back into solution and allowing for a more slower decompression in order to prevent decompression sickness. When divers must work at very deep levels, between 200 feet and nearly 1,000 feet, they frequently live in a large compression tank for days or weeks at a time, remaining compressed at a pressure level near that at which they will be working. So this procedure keeps the tissues and fluids of the body saturated with the gases to which they will be exposed while diving. Then, when they return to the same tank after working, there are no significant changes in pressure, so decompression bubbles do not occur. In very deep dives, especially during saturation diving, helium is usually used in the gas mixture instead of nitrogen for three reasons. It has only 1/5 the narcotic effect of nitrogen, and two, only about 1/2 as much volume of helium dissolves in the body tissues as nitrogen, and the volume that does dissolve diffuses out of the tissues during decompression several times as rapidly as does nitrogen, thus reducing the problem of decompression sickness. The low density of helium keeps the airway resistance for breathing at a minimum, which is very important because highly compressed nitrogen is so dense that airway resistance can become extreme, sometimes making the work of breathing beyond endurance. Finally, in very deep dives, it is important to reduce the oxygen content in the gaseous mixture because otherwise oxygen toxicity would result. So for example, at a depth of 700 feet, a 1% oxygen mixture will provide all the oxygen required by the diver, whereas a 21% mixture of oxygen delivers a partial pressure of oxygen to the lungs of more than 4 atmosphere, a level very likely to cause seizures in as little as 30 minutes. And finally, if a diver is brought to the surface slowly enough of the dissolved nitrogen can usually be eliminated by expiration through the lungs to prevent decompression sickness. About 2/3 of the total nitrogen is liberated in an hour, and about 90% is liberated in 6 hours. Thus, for a work period on the sea bottom of only 1 hour, the total time for decompression is about 3 hours. I would like to mention the references used in this lecture, and all these references are available at Clinical Key, and the articles are available online and can be downloaded for the students' perusal.